Hello, good morning everyone, and welcome to this new LATI webinar. The topic of the day will be quite appealing, I would say. We will talk about advantages and sustainability of thermally conductive compounds. First of all, let me thank all of you for attending the webinar. And as we wait for the last attendees to join, let me introduce a little bit the company and myself. LATI is an Italian-based company skilled in thermoplastic compounds. We are on the market since 1945, and we normally produce high-performance thermoplastics and special compounds for injection molding. My name is Luca Posca. I am the Director of Technical Service, Marketing and Communication at LATI, and today I will be pleased to introduce you to the properties of thermally conductive plastics and how these plastics can actually help you in a more sustainable development of your projects. Now, let's move into the webinar and let's focus on the agenda. We will discuss about 5 main topics. The first topic will be a short resume of what are thermally conductive compounds, how they are composed, and how they do work. The second topic will be about the properties of thermally conductive compound and how they can actually provide staggering improvements to your projects as long as they are properly used in your applications. So we will talk a little bit about proper design with thermally conductive compounds. But the topic of the day will be about the environmental sustainability of plastic-based thermally conductive materials. We will try to better understand what is environmental sustainability and how plastic can actually compete with traditional solutions as metals in developing more sustainable applications. We will talk about the so-called GWP, which is the global warming potential, which is a well-known term describing the way products and processes impact on greenhouse gases generation. And we will try to better understand how thermally conductive compounds from LATI, the so-called LATICONTHER compounds, can actually provide very interesting figures when it comes to the GWP. At the end of the webinar, we will try to wrap up and draw some conclusions about how these plastics can actually provide a very interesting proposal for not only perfectly working, but even perfectly sustainable applications. Now, let's jump into the first topic. Let me please introduce what is a thermally conductive plastic. As you know, plastics are thermally insulative materials. A thermally conductive compound is a mixture between a polymeric matrix, which must be accurately selected. Then you have to put plenty of a conductive filler, which could be, as we will see later, graphite or ceramic. Then you have to be able to properly disperse this filler into the matrix in order to obtain a pellet whose properties can be somehow homogeneous. Our products are called the LATICONTHER, but you will find plenty of similar products also from our competitors. Now, the first 3 steps, so the generation of the polymeric matrix, the production of the conductive filler, and the extrusion of the pellet in itself, contribute to the production of greenhouse equivalent gases. So we will try to understand how these 3 phases actually contribute and how they do actually weight when it comes to GWP. Now, let's understand how these thermally conductive compounds actually work. Now, let's figure out we are able to disperse some filler into a plastic matrix. Let's imagine that these orange bubbles are a conductive filler that we have been able to disperse in a very accurate way in a plastic matrix. What happens when you have incoming heat flux? Well, the heat must move through an insulative matrix, and this can be done only by using the small conductive particles, which are actually capable of transmitting heat. The more you increase the filler content, the more capable your material will be to properly transmit and manage the heat flux. So, as you have already understood, thermally conductive compounds feature staggering high filler content. Today we produce up to 80% of graphite and ceramic to have reliable thermal performance. And of course, you have to be able to select a proper polymeric matrix, because not all polymers can actually be used to produce effective and properly working thermally conductive plastics. Only some of them, like polypropylene, some polyamides, polyamide 12, PPS, and so on. But not every polymer can be used. Well, let's suppose we have been able to produce this highly filled compound. Which are the disadvantages of this kind of product? Well, these products are rather viscous, so they cannot be used for all-around applications. The surface finish is not perfect, and of course, as you can easily understand, the mechanical properties of these compounds are not as good as the proper structural plastics because of the high amount of inert filler that we have been able to put inside. But which are the advantages of these kind of materials? First of all, you have a very high thermal conductivity, 100 times higher than ordinary plastics. Then you have a very good dimensional stability. Your injection molded part will stay flat and will respect the tolerances you have on your drawing because of the higher filler amount. The performance of these materials will last in time. So the thermal conductivity that we have been able to give to the plastic will not fade away in time. It will be constant in time. So you can actually design for part working even in 20 years. Last but not least, do not forget the chemical resistance of plastic, which is actually much higher chemical resistance of metals, especially if you're thinking about applications for outdoor usage or for under the roof where you can have temperature and dirt built up. Chemical resistance is always a very interesting advantage of plastic. Now, we have understood that we have to put a lot of filler into plastic to have a thermally conductive compound, but which kind of filler? You can select from ceramics, which normally are metallic salts or oxides. These ceramics can be effective from a thermal conductivity point of view. They will provide excellent dimensional stability. They are electrically insulating, which is also very important for some E&E application. And you can rely also on some other very interesting properties. Some of these thermally conductive ceramic-based compounds can be flame retardant. They can accept inserts. They can be somehow colored, even if you cannot have full chroma. You can have some faint colors, light colors. And they are clean materials. They will not stain your machine or your application. The other chance we have is graphite. Graphite is an extremely versatile product. Actually, graphite can be electrically conductive, very electrically conductive. The conductivity of the material can be as low as 10 power 4. The thermal conductivity anyhow is really very, very high. This is the highest thermal conductivity that we are able to achieve. It's close to 30 Baton meter Kelvin. They can accept inserts and they can be machined. So from a mechanical point of view, they're very interesting compounds. You can somehow drill holes. You can use screws directly into these graphite-based thermally conductive plastics, on the contrary of ceramic-based, which are more brittle. And then you can also paint them because of being electrically conductive. You can somehow use the modern powder painting techniques. The biggest issue when it comes to thermally conductive plastics is to properly disperse the filler. You have to be able to achieve an excellent dispersion of the filler inside, otherwise the compound will not work. The fillers are very different, not only from a chemical or morphological reason, but also from the shape they have. Ceramics are more or less always isotropic. They are like small spheres, as you can see above. Graphite and hexagonal boron nitride are flake-oriented particles, so they can actually orient during the filling. Why am I saying that? Because the thermal behavior of these kind of plastics, in case you're using a flake-shaped filler, can change quite a lot depending on filler orientation and wall thickness. Let's give a look at these numbers. This is the thermal conductivity in plane. In plane meaning that the flakes are oriented on the plane and we are actually measuring the thermal conductivity in the plane direction. As you can see, the numbers are really very high. Thermal conductivity of a graphite-based fully oriented plastic can be as high as 35 to 40 watt/meter Kelvin. The higher the thickness, the lower the in-plane conductivity. Through plane is completely different. The conductivity through plane, which is actually normally is the conductivity that is used in many applications, is much lower, and it is in the field from, I would say, 3 to 5 watt/meter Kelvin, up to 6, and it will be higher the higher is the wall thickness. But let's give a look at these numbers. We are talking about 40 watt/meter Kelvin. Plastics normally have a much lower figure. Now, let's make the first comparison between thermally conductive plastic and the king of heat management, which is aluminum. Aluminum has a very interesting set of properties when it comes to electrical and thermal conductivity. Let's give a look at that. Aluminum as a die cast, I'm talking about die cast, not elemental pure aluminum. I'm talking about die cast because it is the most used aluminum in a thermal management application. The density of die cast aluminum is 2.7, and its conductivity along plane or through plane, it makes no difference, is 110 more or less, which is lower than elemental aluminum. Elemental aluminum is as high as 200 watt/meter Kelvin, something like that. But actually, we have to focus our attention on this number, more than 100 watt/meter Kelvin. An ordinary reinforced plastics like nylon 66, 30 or 35% glass fiber has a much lower density, but the thermal conductivity is close to 0, 0.1, 0.2, something like that. A thermally conductive ceramic-based, the density is close to 2, so we are getting closer to aluminum, and the conductivity is more or less 10 times higher the conductivity of ordinary plastics, but we are still very far from metal. If we use the, let me say, the high-end ceramic like hexagonal boron nitride, we can rely on conductivity in the field of 4 to 6 watt/meter Kelvin, which is much better than ordinary ceramic, but we are still very far from metals. But let's give a look at what happens when we use graphite-based. For those applications where actually the electrical conductivity of the material is not a problem. What is the performance of these materials? Well, an average, a typical graphite-based thermally conductive compounds has a density between 1.5 and 1.6. So we are close to 1/2 the density of aluminum. And the thermal conductivity is, as we have seen before, from 5-6 watt/meter Kelvin through plane up to 30 watt/meter Kelvin in plane. You may say that these numbers are still very low when compared to aluminum, but we will see that actually in many applications, the higher thermal conductivity of aluminum can be redundant. So we will focus on these two materials here, aluminum die cast and graphite-based thermally conductive plastic compound. First of all, we have to better understand how thermal management actually works. How do the heat flow move through the body of a heat sink? Let's imagine we have this heat sink here, which is actually, by the way, the real heat sink of the Hexagro application that we have shown in the webinars of 2022 and 2021. It is a LED lamp. This is the section cut of this LED lamp. And you can imagine that the red strip there is the heat source. So the first step is to move heat through the heat sink. We have to warm up the heat sink. So the first step is heat conduction. The law describing heat conduction through the body of the heat sink is described here. I do not want to get into the math. I know nobody likes math actually. But I want you to focus on your attention on that red letter there, which is called lambda, and which is the thermal conductivity. Being aluminum, a material with a much higher thermal conductivity, we can say that the first step is won by aluminum. So aluminum will perform much better when it comes to conduction. So the aluminum heatsink will warm up in a much lower time rather than plastic compound. The second step is moving heat from the heatsink to air. And in this case, we are actually facing a redetermining step because it's not easy to convince air or any other fluid to take away the heat. That's the reason why we have a different fluid regime, as we say. We can have natural convection, so we let the air or the fluid move freely around the body of the heat sink and remove heat, or we have the so-called forced convection. That's the case when we use a pump or a fan or an impeller to blow air or any other fluid against the warm body in order to cool it down and remove heat. The law is completely different, and as you can see, the heat transmission is ruled by the red H letter, which is the global heat exchange factor. And in this case, I will show to you later that aluminum and compound perform more or less the same, because the problem is to convince the fluid to take away the heat. It has nothing to do with the material performance, it has more to do with the air or water behavior. The last step is radiation. That is the way that many materials have to radiate heat around them as electromagnetic wave. The law is different, and in this case, the red letter is emissivity. And in the case of graphite-based compounds, we are talking about a deep black material, on the contrary of natural aluminum, which is a silvery, shiny material, unless you treat it or paint it or make some anodization treatment, which is very expensive, by the way. So as you can see, we have a kind of mixed situation. By the way, this is the actual part that we have been describing here, and you can check it out on our website. There are plenty of interesting webinars and project development concerning this very Exagro lamp. Now, let's see how this redetermining step, which is actually moving the heat from the heatsink to air, how this redetermining step is actually the driving force of the whole heat exchange when it comes to natural convection. H, the global heat flux coefficient, is depending on the behavior and the nature of the surrounding fluid, which could be water or could be air. In the case of water, the heat exchange is much higher. But it is possible to demonstrate by an experimental way that this is the redetermining step, and we have to take care of this step if we want to have a successful application. In the case of natural convection, so in the case of parts which are cooled not by fans or by pumps blowing fluids, but as ordinary lamps, they're just left in the open air to cool down. In the case of natural convection and in the case of thermal conductivity above 10 watt-meter Kelvin, it is possible to demonstrate that aluminum and LATICONTHER behave the same. So a metal and a properly working thermally conductive graphite-based compounds, whose conductivity must be at least above 10 watt-meter Kelvin, you will see almost no difference in the behavior of the heat sink, whether it is built with aluminum, featuring a much higher thermal conductivity, or a plastic-based compounds, whose conductivity is lower, but it's actually working properly as well. Now let's give a look, let's try to sum up. When can we use aluminum and when can we use plastics? Aluminum is a winner for all those situations where you have high power concentration, high density of power. You have a lot of heat produced by a single spot, very concentrated. You need an impeller to blow fluid or water or air against the heatsink because you want to keep it cool. So in all the situations where you have a high amount of heat, you need aluminum. You cannot rely on plastics. Aluminum is also a winner when it comes to extruded profiles because it is a very cheap, it is a cost-driven situation, not a performance-driven situation. So in the case of extruded profiles, aluminum is always a winner. When can we use thermally conductive plastics? For all the other situations. So in case of natural convection, In the case of complex geometries, where you want actually to add some features to the original design of the part, which can actually complicate quite a lot the geometry and the mold that you're going to use. For all the situations requiring weight reduction or a very aggressive environment, I want you to focus your attention on the topic of weight reduction, because we will find it later when we will talk about the global warming potential of our processes. Weight is a very important factor when it comes to GWP. Where are we actually selling today the thermally conductive compounds? LED lighting, E&E, electric and electronic sensors, and other applications also in automotive, where you have wireless stuff and applications like that. In many e-mobility applications, there is a huge issue with keeping the batteries at the right temperature, and that's where there is a huge development of thermally conductive plastics, because you want to have a light device properly working. And then heat exchangers in general. There are many applications where you want to remove aluminum or even stainless steel from some heat exchangers. What do these sectors have in common? But not only these sectors, what do all these sectors have in common today? They all must show a much better sustainability, not only of the processes, but also of the end product. As you for sure have already heard from many of your customers or many of the OEMs or end users, the whole the whole Western market is moving in the direction of a much more sustainable development. So how can these plastics actually help you in developing more sustainable and reduce the impact on the environment of your projects? First of all, we have to understand what is sustainability. When a development is actually considered as environmentally sustainable, of course, when it satisfies the needs of the living generation, but it must not compromise the right to the same satisfaction of the forthcoming generation. So it must not deplete the planet assets and resources. It must be respectful of water, of energy, and raw materials, and of course, it must be respectful also of the climate and biodiversity. It is not so easy today to show that our processes are properly sustainable. But now we are going to focus on this concept of efficient use of energy and raw materials, because this is at hand. We can do something about this with the way we choose our materials and with the way we design. How is evaluated the sustainability of your product and your process? By the so-called life cycle assessment, which is a very complicated measurement criterion used to better understand how your process and your product will actually impact on the planet. So the whole process, the whole life cycle of a product is taken into consideration, from the production to the part manufacturing, transport, use, and end of life. And some parameters are very carefully evaluated, mostly related to the way the environment is involved in this process. And the last of these, of course, the last in the order, but not by relevance, is what I told you before, the global warming potential. Let's focus our attention on this topic, the global warming potential. What is the global warming potential? The global warming potential indicates how much a product or a process actually contributes in generating greenhouse equivalent gases. It's very tricky, it's very complicated to evaluate how much not only CO2 but also CO2 equivalent are produced by the whole product line and the whole processes involved in the production of one single device. But it is possible today to measure how much equivalent CO2 is produced in a specific time frame by a product or a process. In the case of LATI, of course, we have to evaluate, as we say, from cradle to gate. So from the production of the raw materials to the moment the compound exits our production facility. The calculation of the global warming potential and related carbon footprint is very complex, is really very complex, takes a staggering amount of time. You have to be extremely careful because many factors are taken into consideration. These decisions can be also influenced by who is actually making the math, but I want you to better understand how this works. The global warming potential is affected by the type of asset that you're actually extracting and the quality of the asset that you are extracting. How pure is your material? How many processes it will require to be properly processed and refined? By the technology and the efficiency that you're actually using in your manufacturing process, by the type of energy that you're actually using. Where does it come from? From renewable sources? Is it fossil fuel based, whatever? And by the type and number of transports. Of course, the more you have to displace your raw materials, the higher will be the impact of your product and your process on the global warming potential. Let's make some numbers. Let's give a look at some numbers. Let's focus our attention on primary aluminum. Primary aluminum means the aluminum that you extract from the cave, from the mine actually, to the first usage. The global warming potential that you can find in literature spans from 5.3 to 41. So you can see how wide is actually the range where the GWP of aluminum expressed as kilogram of CO2 equivalent per kilogram of aluminum it can be. For this presentation, I have assumed a number of 8.5. So I wanted to be fair and I wanted to stay as close as possible to the lowest number of the range. So this is the number that I'm going to consider, but now I want you to focus your attention on the topic of transports, because that's exactly where our plastic kick in, and that's exactly where we are selling and proposing it right now. Why are we talking about transports? Because any weight reduction will provide immediate benefits in terms of fuel consumption. The lighter is your car, is your truck, is your whatever, the lower will be its fuel consumption. And this is absolutely fundamental if we consider that more than 25% of greenhouse gases are produced by transports, and 80% of that 25% is produced by wheel transport. If we are able to reduce steel with a lighter material as aluminum, we can actually reduce the weight by 45%. Let's imagine if we replace steel with plastics, which are actually weighing 1/2 of aluminum. And if we were able to save 10% of weight, we would save 8% of fuel. And this means that we will have a much lower impact on the environment as CO2 emission. Why is this so important? And how can we contribute in reducing the weight of the car or the truck or whatever? If we give a look at this table, I wanted to gather actual figures of a C-segment car weight, year 2023, the same model, different engines. You can see that the difference in weight between a traditional gasoline gasoline fueled engine and a full electric car, same car, same power, same model, same year, is 30%. So the more we move in the direction of hybrid and electric, the higher is the requirement of lightweight parts. And that's exactly where plastics kick in, and that's exactly where plastic can make the difference. E-mobility and hybrid mobility. Let's make an exercise. Let's suppose we are able to replace steel using nylon 66 and 40% carbon fiber, typical injection moldable or composite, whatever. The weight reduction is 70%, but of course it is mandatory to re-engineer the geometry of the part because you need the same structural performance. So you need to change the geometry of the plastic part. You will have to increase thicknesses, put ribs or whatever. So you have to take into consideration what is called the material index, describing how much mechanical performance is actually delivered with that very material. And the numbers say that you can have a much more favorable material index when it comes to carbon fiber reinforced plastic versus traditional materials like aluminum. So you will have more strength with lower weight using carbon fiber reinforced plastics. But how does it work? It is mandatory to re-engineer your part. Focus your attention on this topic because it is very important. For structural plastics, you need to re-engineer your part, and this can mean changing the geometry. It is a big effort. It is not easy. It is not straightforward. You cannot use one-to-one plastic to metal replacement in the same geometry. You will have complete failure. You need to redesign your part. Now, let's translate this exercise from structural metal to structural plastic, and let's evaluate the global warming potential reduction. Let's evaluate the cradle-to-gate global warming potential of aluminum and plastic. In the table you see here, in the chart you see here, you can see actual numbers which can be found in the literature. For aluminum, I wanted to include 60% of scrap aluminum in a die cast. So the global warming potential for die cast aluminum featuring 60% of recycled is more or less 4 kilos of CO2 equivalent per kilo. Remember this number, 4 kg of CO2 equivalent per kilo of aluminum using 60% of recycled. I know that today some die cast can be 100%, but let's focus our attention on this 60%. What happens with nylon 66 featuring 40% of recycled carbon fiber? The global warming potential is 2.8 of the CO2 equivalent per kilo. Per kilo. It means that then we will have to take into consideration also the density of the materials to have the proper global warming potential of the very application. Okay, we have understood how it works. So now exercise 2. Let's evaluate the global warming potential of thermally conductive plastics, because that's exactly what we are here to talk about. We have focused on two of the best-selling LATICONTHER compounds, nylon 6 and 50% graphite, polypropylene with 70% graphite. For the nylon 6, you can see that the formula includes nylon 6 and 50% of natural or synthetic graphite, whose global warming potential is kind of different, but it's more or less from 3.5 to 4. The global warming potential is 6.5 to 7 of CO2 equivalent per kilo. If we move to polypropylene, this number can be vastly reduced because polypropylene has a very low CO2 equivalent production when is manufactured. So the global warming potential of a 70% based polypropylene thermally conductive compound is 4.5 to 5. If you want, you can also add an extra 0.3, 0.4 kilogram of CO2 equivalent per kilo for the injection molding process, which will be not only from cradle to gate, but also the next step, which is actually manufacturing. Now, if we look at this number and remember the 4 of the die cast, we may ask, okay, so what's the point? The point is that you have to consider the density of these materials. So for a proper part, for an application, as the LED light seat you see here, you have to evaluate the global warming potential of a functional unit. So you have to evaluate the global warming potential per volume, not per kg. So that's exactly where density difference kicks in. If we make the math, we can see that aluminum, the global warming potential for the very part, same geometry, same volume. Even if we include the 60% recycled aluminum, the global warming potential is 10.8, and plastic is below that number. Please note that I am talking about virgin plastics. I'm not talking about recycled plastic. I'm talking about virgin base resin and virgin graphite, on the contrary of aluminum, which is 60% recycled. Very interesting numbers, isn't it? Very, very interesting numbers. So if we imagine to move aluminum to LATICONTHER, to thermally conductive plastics, which would be the advantages in the application, in your very application? The thermal performance requires no material index. You remember that we have been talking about material index. What is material index? Is the amount of mechanical performance that you can use per kilo of material, of course, and that requires a redesigning of the part when it comes to structural application. For thermal performance, you will not need to change the volume of your part to have a properly working thermal management application. The geometry can be the same. Actually, it can be lighter than metals, because you have to change something to use maybe graphite orientation. So you will not be required to add volume to have proper performance. Your car featuring plastic parts, of course, will consume a much lower amount of fuel, and this will, of course, have a very big impact on the global warming potential of the full process, which also includes many transports. The higher is the graphite content, the lower will be the GWP when it comes to high GWP producing base resins like polyamide 6. And last but not least, we have been talking about virgin plastics. But what if we were able to use recycled plastics into our compounds? And this will be the booming topic of the next years: recycle, and recycle again. We wanted to move forward, and we wanted to evaluate what happens when we recover thermally conductive plastic. So we tried to injection mold LATICONTHER based parts, nylon 6, 50% graphite. We grounded them and we injection molded them more times. We found out that thermally conductive is not affected by the usage of reground and recycled thermally conductive plastic. As you can see, the numbers are more or less the same, using 25% of recycled or 100% recycled. Also, mechanical properties stay more or less the same, but I want you to focus your attention on thermal conductivity. This means that you can actually be able to recycle thermal conductive plastics into virgin thermal conductive plastics with no diminishing, with no decaying of the thermal performance of your part. This means that these plastics are the best candidate to recycling. That's the reason why we are moving also forward in this evaluation, and we have also made some calculation about this. Now, let's sum up. Let's face the difference between aluminum and graphite. Let's talk about the processing. When it comes to processing, you also pay the electric bill, let me say, and you also have to pay the maintenance of your equipment. When it comes to processing, the difference is really outstanding. The melt temperature aluminum versus graphite is 700 degrees versus 250. The mold temperature is very different as well. The mold life expectancy is extremely different. If you are very good at die casting, you can rely on maybe 30 to 60,000 shots. With plastics, you can rely on more than 500,000 shots. But I am aware of molds lasting 2 million, 1 million shots. The minimum wall thickness that you can fill with aluminum is more or less 1.5, but with these thermally conductive plastics based on graphite, you can go well below 1 millimeter. The post-molding processes can be very expensive for aluminum, and they are not necessary for graphite. You pull out from the mold the finished part. There is no more sandblasting, despruing, there is no more painting, there is no more washing, there is nothing. You pull out from the injection molding tool, you pull out the finished part. You can have some issues with aluminum, warpage, voids, depending on the way you cool your part down, on the contrary of nylon-based and graphite-based compounds, which can be mechanically brittle. This is the main disadvantage. And last but not least, talking about scrap recovery, aluminum can be fully recycled, but you have to remove slags from the freshly new melt scraps, and this also impacts on the global warming potential. For compounds, you can recycle it 100%, but we normally suggest never to exceed 25 to 50%. So, advantages and disadvantages. I leave to your judgment this chart here. Let's talk about money. That's a very important topic. Let's talk about the raw material cost. These figures are up to date at the beginning of, let me say, April 2023. So maybe they could be a little bit old right now. But when we talk about aluminum density 2.7 and the polyamide 6, 50% graphite density 1.5, the cost euro per kilo of aluminum is from 2.5 to 4. Polyamide 6, 50% graphite from 6 to 7, depending on the amount of product that you purchase. So if you do the math, you multiply by density, you see that the cost of the raw material per cubic decimeter, that's actually the cost per volume, is competitive. So also not only from a performance point of view, but also from a GWP point of view and from a cost point of view, thermally conductive plastics can be a winning choice. And it would be even better if we were able to properly recycle them. Today, the design for recycling is a major topic. Lati will be involved the next week in a presentation in Munich at the AMI convention, talking about this design for recycling. This is the most challenging topic for the next future. Our end products must be conceived, must be designed for the further recycling, not only the plastics, but also the end products. If we were able to properly design parts for end-of-life recycling, we could use this plastic into virgin plastic and furtherly reduce the global warming potential. In this slide here, you see as an example the first concept of this LED lamp using 3-4 different materials, and the finished products using only one material. And this is what I say, design for recycling. So we are at the end of our webinar. I would be pleased to draw some conclusions with you. Now, moving from metal to plastic will allow a much lighter, versatile, and effective solution in case of natural convection, of course. The thermal performances will be as good as metal. Even if the numbers are lower, the thermal performance will be the same because of the rate determining step, which is convection. The global warming potential will be lower thanks to the numbers of plastics and to the lower density and the lightness of the solution. Not only from cradle to gate, so from the extraction of raw materials to the production of the new compound, but also from cradle to gate, which means from the extraction to the grave of the end of life of the product. Plastics are fully recyclable, and last but not least, the bottom line cost can be extremely competitive. So I really hope I was able to give you a decent introduction to thermally conductive compounds and how these compounds can, let me say, can support your application, can application not only in managing heat, but also in reducing the amount of global warming potential. Now I will welcome your questions. I will be extremely pleased to answer your question. I see we have 7 questions. Let me start from the very beginning. How do you know or control the orientation of the filler particles? Very good question. Lati today can, not only Lati, I suppose, but from the year 2017, we have shown that we can simulate the particle orientation with a finite element injection molding simulator. We use Moldex 3D. And with Moldex 3D, you can actually see how the flakes will orient in the part. And then you can post-process these numbers into a thermal simulator, and you can actually describe the performance of the real part, not as an average part, but the real part. If you check our website in the ebook part and the event part, you can see the recording of a webinar, of a couple of webinars actually we got in year 2018 at AMI and during year 2021, 2022, where we carefully described this process. I really recommend that. It's very interesting and results can be really, I would say, inspiring to move in direction of plastic, carbon graphite-based plastics. Second question, did you test plastic in space and vacuum? Well, actually we did. We did with some partners in England and in Europe. And the results are the ones that I've just shown. Emissivity of this of graphite-based thermally conductive plastic is more or less, as I say, 0.85 or 0.89, something like that. And we measure the conductivity as well in air and in vacuum as well. Another question, how do you mix 80% of graphite or mineral filler into the polymer? That's a very, very smart question. We have a twin screw extruder. I can share with you some details about the manufacturing process, but actually dispersing 80% of ceramic or 70% of graphite into plastic is really one of the pillars of the know-how of the company, because you can do it with many plastics, but not with all plastics. 70% today is possible in LATI with polyamide 6 and polypropylene. We can go up to 70% with some other resins like PPS, but the average is 50%. Dispersion is really the very demanding process. It's very, very complicated. I think we had a very important exercise with carbon nanotubes. That's the kind of filler where we improved a lot our know-how, the geometry of our screws, and the way we set our extruder. Carbon nanotubes can be the most challenging, actually, I would say, filler to be properly dispersed. Then it comes to this amount of metals or fillers. You need the proper resin and you need the proper equipment, but you cannot do it on all plastics. I would say at least we were not able. I've seen on the market some of our competitors were able to introduce more than 80%. And that's really, really appealing, I would say. Fourth question, how abrasive are the graphite or the ceramic particle on the tooling? Very good question. Ceramics, many of the ceramic particles can be abrasive. Of course, if you already have an experience with glass or carbon fibers, you know what I'm talking about. Ceramics can be abrasive. Graphite normally is not very abrasive. It's a rather soft filler. So graphite is normally not a problem. Ceramics can be more a problem, especially in the case you mix ceramics with flame retardants, glass. We have some glass fiber filled flame retardant thermally conductive plastics which require hardened steel with some surface hardening like titanium nitride or stellite deposition, PVD deposition. Graphite is normally not a problem. Ceramics can be something to be properly managed. Another question, what is the average thermal conductivity in case of molding process in general? Okay, very interesting question. In case of an isotropic filler, like ordinary metal oxides or metal salts, barium sulfate, just to name one, or zinc oxide or whatever, they are isotropic. So the number you can actually achieve on your part is more or less 1 to 2 Vaton meter Kelvin, and these are isotropic. So you can rely on this kind of conductivity, never minding the direction in space. When it comes to graphite, this is much different. As you can see, the number can span from 3.5 to 40, depending on the flake orientation. We made some evaluation, experimental and numeric simulation, and we consider a number more or less from 8 to 10 to be a decent and reliable thermal conductivity value for an isotropic approach, even when you are using a not isotropic filler. Of course, you need to have at least an average wall thickness from 2.5 to 3 millimeter. For higher than that or lower than that, the situation can vary, especially if you're using very, very thin walls. But if you're using a wall thickness from 2.5 to 4, well, I would say that a number from 8 to 10 watt per meter Kelvin can be a generally very reliable isotropic approximation of even from a non-isotropic filler. Okay, tell me the smallest possible wall thickness to guarantee that enough particles are inside. I would never recommend to go below, let me say, 0.8 millimeter, because we are talking about very, very small particles. Graphite is really very small. I cannot remember the figure, but it's in the field of some microns. It's really very, very small. So you are not in the situation of properly reducing the amount of graphite going down with thickness. The problem is that the lower is the thickness, the higher is the orientation in plane. The higher will be the orientation, the thermal conductivity in plane, the lower will be the orientation through plane. So very thin walls can move heat very efficiently in plane, but not very efficiently through plane. So I would never recommend to go below 0.8. We have filled down to 0.5, the parts still work. But if you want to have a nice figure, I would say 1.5, this could be an excellent, a decent figure. Is it possible to have graphite and glass fiber to get specific mechanical properties? Very good question. The answer is yes. In the past, we have produced for the automotive, especially for the automotive sector, a few grades which were actually featuring they were more or less a compromise. You could have two answers. Let's say 15% glass and 35% glass, and then you put 40% graphite in the first one and 20-30% graphite in the second one. So you can mix graphite and glass fibers. You will have a compromise. You will have a better thermal conductivity, but you will not have a properly thermally conductive product. You will have something that stay more or less in the middle. If you want to check on our website, you will find out some press releases actually released, I would say, a few years ago, because before the COVID. The products are called LATICONTHER MI01 and MI02. I will send you the press release and the technical data sheet. I can see your email, so it will be my care to send you the technical data sheet and the press release where we describe this kind of products, which were actually developed to have structural performance and thermal management for automotive applications. Then other questions. 3D printable thermally conductive. Yes, we have an experimental grade featuring ceramics for filament fused deposition. But if you are able to 3D print from granules, then the answer is yes, because thermally conductive plastics can be used as pellets for filament deposition from pellets, from granules. And the results are really very, very interesting, also from a thermal conductive performance point of view. Okay, the last question here I have is about, okay, are there flame retardant thermally conductive compounds? Yes, as I have already said, we have both graphite-based and ceramic-based flame retardant compounds, thermally conductive compounds. If you check our website on the LATICONTHER for the LATICONTHER in the LATIMaterial database, or if you check the UL database, you will find 3 or 4 thermally conductive compounds which can offer a full V0 compliance down to 0.75, something like that. So yes, we can propose both graphite and ceramic based thermally conductive compounds, also flame retardants. Oh, another question, the last one that jumped in, then our time is over. What is the GWP of LATICONTHER with recycled plastic inside? Well, we did some math. I can share with you a number. If we were able to put, let me say, 50% of recycled LATICONTHER, 62%, 62 with 50% graphite in virgin LATICONTHER, the global warming potential will be reduced down to 3.5. So this is another very, very interesting figure. And we do this math in a very fair and conservative way. We want to stay, let me say, I do not want to brag on that. I want to say 3.5, hoping that maybe it's 2.5. Okay. So thank you for attending. Our time is over. I welcome really all of you who have been able to stay with me for the whole time. I really appreciate that. I really appreciate your attention. I really hope I was able to give you a decent introduction to the topic. Please email me or our people for any other question. I will welcome all other questions. I will respond, I will answer via my email. And if you want to spread this webinar, please remember that you can check out our social media channels, LinkedIn or YouTube. On YouTube, on Lati YouTube channel, you can find all the webinars that we gave in Italian, English, French, and German. And you can maybe use it also for training in your company. Thank you so much, and keep your antennas up, because before the end of the year, because the end of summer shutdown, sorry, another webinar will be given. The topic is still under construction, but it will be interesting. So thank you so much. Thank you so much for your time, and see you soon at the next webinar. Bye-bye.